Hello everyone, I'm Changcheng, and today I want to present you our project in WCV regarding object-centric video representation for long-term action anticipation. First, I want to give you a brief talk about long-term action anticipation task. Given a video observation captured in first-person view, the long-term action anticipation is defined as generating an action sequence of the camera variable in the form of verb and object pairs over a long time horizon into the future. In specific, the learned model is expected to predict a sequence of Z action in the form of object and verb pairs, giving visual observation up to time Tj in the video. Tj is the end time for the J's label segment in the original video. During evaluation, the added distance between a predicted sequence and the ground truth sequence is computed. To account for uncertainty in action anticipation, the model can predict up to K sequence for each input example. So our motivation comes from the object which interacting in the real world. As illustrated, our key motivation is that a detailed object-centric understanding of the scene provide visual clues on the growth of the action and available tools to recognize and predict human-object label interaction, especially when the predictions are longer term, as an observed background object could be used by a human actor in the future. We also know that existing object-based video recommendation frameworks either assume the existence of in-domain supervised object detector or follow a fully weakly supervised pipeline to infer object location from action labels. So we propose to build object-centric video representation by leveraging visual language pretrained model. This is achieved by our object prompts, an approach to exact task-specific object-centric representations from general proposed pretrained framework without actual fine-tuning. In specific with this illustration, we show that the input image and the list of objects of interest selected based on domain knowledge using our object prompts. The prompts are then provided to a frozen visual language model, such as GLIP, to detect the objects of interest and extract object-centric visual representations. Then we have our overall model architecture is to recognize and predict human-object interaction. So we instead use a transformer-based neural architecture which allows the retrieval of relevant object for action anticipation in various timescales. We extract the video representation eclipse using a pre-trained video encoder. We use the object prompt to select and extract object-centric representation E-object from videos. After that, we are using our predictive transformer encoder PTE encodes Z learnable token E position to compute the future E feature for action anticipation. A decoder in the network is applied on the E feature to predict action, which is verb and object pairs. We then get a lot of competitive results from our experiment conducted on 3 major datasets. For Agarwal, we are doing long-term action anticipation, which we report at the distance as our matrix. And for 50 seller, we also use their long-term action anticipation result by compare with the main over class accuracy, which is their normal LTA evaluation matrix. For both of the dataset, we retrieve competitive result, which nearly sort of are. For EGTEA Gaze Plus, we actually doing the next action prediction result, which also receive competitive results. We also perform actual ablation study for our transformer-based model architecture and also our object prompt. In our case, PTE outperforms the baseline temporal aggregator by a large margin in both verb and noun. And also we can find the object-centric representation extracted by object prompt can effectively improve the performance, especially when doing with early fusion. On the right side, we can see the object-centric representation have a high impact. Incorporating clip object embedding brings additional performance gain over clip. Thank you for your listening.